Hello and welcome to my channel. In this series I take you through past VCAA Maths Methods exam questions and provide you with my full work solutions. In today's video we're going through question 8 of the 2020 exam 1, so that's the Calc 3 exam. It's the final question, so it's relatively challenging. Hopefully you guys have had an attempt of this question so far. If not, you'll find a link in the video description. In the video description you'll also find timestamps, so if there's any particular parts you want to skip to, feel free to go ahead and do that. So let's get started. Question 8 reads, part of the graph of y is equal to f of x, where f spans from 0 to infinity, and the function f of x is described by x times log e of x is shown below. So it looks sort of quadratic looking. We've got a couple of points marked in, origin, point Q, and x-intercept at B. The graph of f has a minimum at the point Q. As I just mentioned, find the coordinates of point Q. So hopefully you see the word minimum and you think, that usually ties closely in with the derivative, and more specifically where the derivative is equal to 0, right? So minimums and maximums and stationary points of inflections are exactly that. They're stationary points. So I guess the first thing that we'll start off by stating is pretty much that exactly. So I guess we put min when the derivative is equal to 0. And we want to solve for that essentially. So what do we know about the function f of x? Well, it's actually the multiplication of two different functions, right? We've got x times log e of x. So hopefully that makes you think of the product rule, product meaning actually multiplication. And you'll find that on your formula sheet. There's a particular form that I like to remember it in, and it goes something like, not inverse, f dash of x, and I put inverse before, sorry, been a long day. Okay, f dash of x is equal to v plus of, where u would be the first term, x, u dash is its derivative, would be 1, v is obviously the second term, log e of x, and its derivative would be v dash, which would be just 1 on x. So if you go ahead and you substitute that in, you'll get log e of x times 1 plus x times 1 on x. So x times 1 of x is also just 1. So doing that, we've got log e of x plus 1, and we said before that's when this derivative is equal to 0. So now we just need to solve for x. So we subtract 1 from both sides and then put it into the exponential form. So minus 1, and then convert to exponential, we'll have e to the minus 1 is equal to x. So that would be that point 8 there, and then we just need to find the corresponding y value. So subbing it into the f of x function. So we've got f of e to the minus 1. So we've got e to the minus 1, log e to the minus 1. So we can take this minus 1 out, and we'll have log e of e, which is just 1. So this here is just equal to minus e to the minus 1. So essentially our point Q would be e to the minus 1 minus e to the minus 1, just like that. Hopefully I can do a nice little box around it. Great. Not too bad so far. Moving on to question B. Using the fact that the derivative of x squared log e of x is equal to 2x log e of x plus x, show that x log e of x has an antiderivative of x squared log e of x on 2 minus x squared on 4. So essentially what this question is asking us is it wants us to show that x log e of x, which remember that was our function of f of x. So show that f of x has an antiderivative of this. And they're giving us some extra information to help us solve it. So hopefully you guys can sort of pick up on that this will be an integration by recognition question. And usually the first thing that I like to do is to re-express the information that they've given us to start with. So if we take the integral of both sides here, and that'll be our first step, so we'll notice that the integral here cancels out with the derivative. So we'll have x squared log e of x is equal to the integral of 2x log e x plus x dx. That's the first step, and you can see x log e x, well that term is actually here, but there's a couple extra things like an extra plus x, and it's also multiplied by 2. So if we rearrange it, we want to obtain the integral of x log e of x. So we can do that by subtracting the integral of x from both sides and then dividing everything by 2. So I'm going to try and skip some steps. Definitely encourage you guys to not skip steps. Write down all your workings, but for the sake of time, I'll see if I can save a little bit. So we'll have x log e of x dx is equal to half times x squared log e of x minus integral of x minus the integral of x would be x squared on 2. Something like that. Hopefully I've done it right so far. I think that looks okay. So then going one more step, we will get x squared log e of x all over 2 minus x squared on 4. And you can see we've met requirements here. Our answer is in the same form that was specified. So sometimes it's good to put as required for show that questions. Great. Moving on to question C. Find the area of the region that is bounded by f and the line x is equal to a, and the horizontal axis for x spans between a and b, where b is the x-intercept of f. So we've got the x-intercept f, and we want it spanning between a and b. So if I just zoom in on this area here, the way I'm understanding it is it's between the x-axis, the function, and sort of that area that I'm drawing there. I'll just sort of shade that in. So since it's below the x-axis, the error would be negative, so we need to multiply by a negative to sort of counteract that. And if I go ahead and just set up the integral nice and simply, so the area would be equal to minus the integral between b and a of the function f of x dx. So first line, not too intimidating. Now we go and we sub in our values for a, b, and the function f of x. We know the function f of x is just this x log e of x. A, we worked out in question A, is e to the minus 1, and b, well, you guys might need to do some workings to work that out, but b will be equal to 1. Why is it equal to 1? Well, we know it's equal to 1 because that's dictated by the log term of this function. So when we've got a log where x is equal to 1, the whole log goes to 0. And since it's an x-intercept, we know the same property applies. When b is equal to 1, or the value of x is 1, even though the first part would be equal to 1, this other term brings it to 0. So I'll go ahead and I will write in the next line. So we've got minus between 1 and e to the minus 1 of our function x log e of x dx. Cool. And in part B, we actually worked out what this integral is, or an integral. So obviously in part B, we could have a plus c, but it just is an antiderivative. So we just picked the one without. So we can use our workings, is the point of this. And we just put some brackets around here, and then we'll sub in those values. So, minus x squared log e x all over 2 minus x squared on 4 between 1 e to the minus 1. I'm going to skip some steps. That's just basic sort of subbing in and evaluating at this point. So once you do that, you should get, I got, my first answer was minus 1 on 4 minus 3 on 4 e to the minus 2. And then what I did is I just brought everything over the same denominator. Yeah, so multiplied everything by e squared. And then doing that, we'll have e squared minus 3 all over 4 e squared. Great. Okay, on to D, the final part of the final question. There's I and I for this. So find the value of k for which y is equal to x squared is tangent to the graph of g. And I missed this bit. G here, let g be defined as the function that's limited from a to infinity. So we're just looking at from that local minimum onwards. And it's a translation, a vertical translation up of k units is what g of x is defined as. And we want the value of k for which y is equal to 2x is tangent to the graph of g. So it's tangent to the graph of g. So essentially, this is f. G is a translation upwards that only spans from this point onwards, something like that. Right? Let this be g. And we want that function g to have the tangent y is equal to 2x. So y is equal to 2x. So just draw an approximation for the line y is equal to 2x. Something like this. So y is equal to 2x, passes through the origin. So how we need to find out what the value of k is that satisfies y is equal to 2x being tangential to g. So you can see how I've drawn it. It's not a tangent, but if I shifted it up slightly to say this point here, all of a sudden it is a tangent, and it's also a vertical translation of the function f. So a little bit to digest, getting pretty tricky. You know, obviously it's one of the final questions on the exam, but you can see that at this point of intersection, the gradients are the same, right? That's what tangent means. So scrolling back down. So it's really reliant on using our understanding of the tangents and equating the gradients at this point in time. So we know the equation or the gradient of the tangent, right? Because it's got the same gradient as this straight line. So gradient of tangent is just going to be equal to 2. And then if we equate that, we want to find out some coordinates, right? So by comparing coordinates, we can then work out what the vertical translation is. So that's coming at it from one angle. Coming at it from the other angle would be to work out the derivative for g of x, which is actually ends up being the same derivative as f of x, since there's only a difference of a translation in units between them, right? So that's actually really important to sort of make a distinction between, but we're solving for x when the gradient of these functions is equal to 2. Okay, so I think we worked out the derivative earlier. In part 1 it was, and we had log e of x plus 1 is equal to 2. So subtracting 1 from both sides and then rearranging it, we'll get x is equal to e. I think that's right. And then if we sub that back into the original function f, we'll be able to work out a set of coordinates. So f of e is equal to e log e of e. I think that was it, which is just e. So the coordinate that we pass through is e of e, right? So what that essentially says, at this point over here, e, the function f has a gradient of 2, right? So then, if we translate this up, that we can work out g, right? So I guess it's a little bit tricky to explain, but if I was to draw another tangent on the function f at this point, it would run parallel to the function y is equal to 2x. And then, so what we could do is we could finish working off the equation of this red line. We already know it has a gradient too. We know a point that passes through it, so we can work out the rest of the equation, and then we can translate it up however many units to get to y is equal to 2x, which passes through the origin, and then we'll be able to compare that difference to work out what k, the translation, would be. So hopefully by the visual representations helping a little bit there. So we'll need to finish off working out the equation of the tangent. So y of t is equal to 2x plus c. We know it runs through the point e. So then we've got e is equal to 2e plus c. So C would be equal to minus E. So therefore the equation that we worked out, this is tangent to F, is equal to 2x minus E. So I'll just quickly jump up to this for the one last time. So we know this red line is the tangent for F is equal to 2x minus E. So if we translated it up by E units, then we'd get to the function y is equal to 2x, which meets the requirement for function g. So the translation between the tangents would be the same as the translations between the functions f and g, since they're tangential to each of these functions individually. So again, quite complicated. Don't be too disheartened if it doesn't make complete sense at this point. Just keep trying to work away and visualize things and come at the question from a different angle. Okay, so I guess we know the function, the tangent for g was equal to 2x. So therefore k is equal to E. I guess you could say this here is equal to YTF plus E, right? Where E is equal to K. Something like that. I think the rest of our workings make it clear. And that's only with 1 mark, right? So obviously quite a lot to get to that point. Okay, very lucky last question. Find all values of K for which the graphs of G and G inverse do not intersect. So this one's really particularly quite challenging. And we need to take a similar approach to this question as we did to the previous one, which was comparing the gradients of the function. So we know functions and their inverses usually intersect along the line y is equal to x, right? And usually that property is something we exploit when trying to work out the points of intersection. So you might think, well, let g equal to this function here. But instead, how I was able to solve this problem was by comparing the derivative of g with the derivative of this function y is equal to x, right? So y dash, where the derivative again is like we worked out before for g of x, plus 1, and that's going to be equal to 1. Something like that. Okay, doing that, you'll be able to subtract 1 from both sides, solve for x, and you'll get x is equal to e to the power of 0, which just means x is equal to 1. And then subbing that back into the function. So remember before, I said the derivative of g dash x is equal to the derivative of f dash x, because of the translation, when you take the derivative of a constant, doesn't make a difference. It's 0 either way. So that's the reason why we then sub x is equal to 1 into the original function f of x, and doing that you'll get that's equal to 0. So that's our point that we need to use, and then again we go through a similar set of steps, work out the y, I guess it's like tangent to that point, or it's the equation I should say. Y is equal to x plus c, since it's gradient 1, and then sub in that point, you'll get 0 is equal to 1 plus c, so c is equal to minus 1, so this equation here, y is equal to x minus 1. So what does that tell us at that point in time? I think again it's easier to try and visualize these things. If I get rid of these lines for a second, so we've got the line y is equal to x here. If we know the function g and its inverse, if they intersect, will intersect along this line y is equal to x. But if k is large enough, the g becomes this way, its inverse becomes outwards, and they will never intersect, right? So we trying to find the point where g exactly intersects. We're trying to find the point of k for which g exactly intersects with this line. And then if we do that, we can say the translation needs to be greater than that. So in that way, it's similar to the previous question. we've worked out it's at this point here where the gradient is equal to 1, right? So we've got parallel lines at this point, and we know this function we just worked out to be x minus 1. So therefore, what we know is if we translate up by 1 unit, the gradient of this function will be equal to the gradient of function g, which tells us if g translates up by more than 1, they won't ever intersect, which is what this question's asking for ultimately. So that pretty much is the answer. It's the same sort of logic as what we had before. So k is greater than 1 for no intersection. Again, really challenging. Not many people would get this right, and we'll have a look at what the examiner's report says. Don't be too disheartened if it still doesn't make any sense. Very challenging questions. So jumping back up to question A, what does the examiner's report say? Mostly answered pretty well. We have 59% getting full marks, nice easy marks. Most common errors were the incorrectly finding the derivative or the evaluation, subbing it in at that point there, but generally pretty good. Part B, we've got 36% getting it right, which is relatively good. Many students made up their workings as the answer was given rather than clearly demonstrating, so it's really important to have a clear process with your workings. I would have included a couple more lines if I was actually doing it. Use the lines as an indication of how much workings you should be doing. Obviously, you don't want to, if you know how to answer this type of question, you don't want to miss out on the mark because you haven't done your workings properly. 8C. Only 11% of the state got the full marks for this one, and about a quarter got 1 mark out of 2. Many students were unsure of which terminals to use for the definite integral and opted to use a generic A and B. And yeah, it mentions that was a common oversight, the fact that the error was below the x-axis. So some people omitted the negative. So I don't think this one's particularly difficult. I guess I understand what the examiner's report's mentioning by point B. You do need to put in the exact values for what A and B are, right? Relate everything back to the specific data that you've got, the function. Cool, and moving on to D. We had 16% get K is equal to E, which is not too bad. Many students did not even attempt the question, and those who persisted recognized that the gradient was 2, though often gave an incorrect answer of X is equal to E. Okay, yes, so there's sort of, some people might have got confused with what we're actually trying to work out here. It's actually in terms of K, right? It says find the value of K. So that would suck if you've got E as the answer, but then you put X is equal to E. To go to all that length. I guess those people might have only got to that step, but overall, yeah, not too bad, considering that most people do leave most of these questions blank. So very final one with 2 marks. You can see 95% of the state got 0 for it, and there's only 3% that got full marks, 2% got 1 mark. Some students tried to algebraically find the point of intersection of the graphs of the function and its inverse with limited progress. This question could also be solved by consideration of a point where the gradient, g of x, was equal to the gradient of y is equal to x. So that's what our approach was there. So I think that's probably the best way. Yeah, if it didn't make sense there, recommendation is just to sort of keep drawing these things out, playing with them, thinking about them. I think it's really hard just to take a purely algebraic approach for complex problems like this. I'm definitely a visual person, so I like to draw everything out. Okay, that does it for this video, guys. Hopefully you got something out of it. If you're new to the channel, please leave it the thumbs up. I make content like this fairly regularly, at least a video a week. If you've got any specific questions you'd like answered, then I'm happy to make a video and post it on the channel so you and your friends can get some benefit out of it. If you do have any questions, then please email me at yourmathquestions@gmail.com, and like and subscribe. Thanks for watching, and I'll see you in the next one.